Hello, everyone. Today we are going to talk about complex zeros and fundamental theorem of algebra. We're going to start with that fundamental theorem of algebra. I'm going to write it down like this. Sorry, I want to do more text. Fundamental theorem. Why it's so thick? Okay, I see. Fundamental theorem of algebra tells that every polynomial Pn of x with complex coefficients mean that this an minus 1 up to a0 can be complex numbers. They don't have to be, but they can be. They are allowed to be complex numbers. With complex coefficients has at least one complex zero. Why this theorem is important to us? Well, guys, remember we have factoring theorem. Factoring theorem tells that if let me erase this. If x equals c is 0 of polynomial Pn of x, then you can always represent this polynomial as x minus c multiplied by q of x, and this polynomial is going to have degree n minus 1. Why does it happen? Well, if it's a 0, remember that you plug 0 into here, and it's supposed to give you a result equals to 0. So, which means that when you divide by x minus c, the remainder, which is supposed to be here, right? If you divide by x minus c, there is a quotient q and the remainder. But in special case, when x is a 0, if you plug c over here is going to give you 0, the whole term, and this must be 0 just because it's supposed to be equal to 0. So this must be 0. There is no remainder. So you can always represent it. For us, representation is not important, but it's important that it's going to look for us like we factored the polynomial. We factored out x minus c, and the polynomial, which is a quotient, is going to have a lower degree because otherwise it's not going to be multiplied by x and give you degree of n. Well, what we can do with this polynomial, which is kind of quotient, we can again apply this theorem that it has at least one complex zero and factor that next complex zero and repeat it until we factor all of them. And it's going to give us complete factorization of the polynomial. So complete factorization . It's also theorem, but we are just going to write down that we can always factor a polynomial Pn of x, which is going to look like an x to the power of n and all other terms until we reach a constant term into coefficient a, x minus c1. Sorry, my parenthesis looks like 1. X minus C2. Well, I just factored the first 0 and then the second 0 and then the third 0. And I don't know how many I'm going to have, but eventually I'm going to have the last one, 0 number n. So this over here in this factoring C1 and Cn can be complex numbers. They can be real numbers too, because real numbers are complex numbers with imaginary part equals to 0. So can be complex numbers. A0 is a coefficient not equal to 0. Well, how it's going to help us? Well, we can just, using this theorem or kind of basing on this theorem, factor polynomials completely. I'm going to start with several examples. So example, sorry again, very wide. I think I made my squares or somehow everything is smaller, and that's why my ink is thicker. So let's consider polynomial p of x equals x cubed minus 3x squared plus x minus 3. I want to factor this polynomial completely. Well, remember that if you look for rational roots, which is kind of first thing to do, you are going to look at number 3 and the coefficient of x is equal to 1. And because number 3 has only plus minus 3 factor and plus minus 1 factors, so you think, okay, what is going to be the simplest rational root to check? And of course it's 1, right? So I'm going to check actually 1. I'm going to use my synthetic division, so copy the coefficient of x cubed, coefficient of x squared, coefficient of x, and coefficient of no, this example I just wanted to factor. I didn't want to do the division. Okay, let's do the division. I don't know. Let's check 1 first. Minus 3. It's kind of, I forgot that this one was designed to factor it just like by looking at it, but let's check 1. Is 1 going to be a root of this polynomial? Well, let's remember synthetic division. You copy 1 over here down. 1 by 1 is 1, and 1 plus minus 3 is minus 2. Minus 2 by 1 is minus 2. Minus 2 and 1 is negative 1. 1 by negative 1 is negative 1, and we get negative 4. This is a remainder which is not equal to 0, means that this is not 0. Well, I'm going to try now 3. Let's see if 3 is going to work. So I know that plus 1 is not 0. How about plus 3? Let's see if plus 3 is going to be 0. So again, the synthetic division, 1, negative 3, 1, negative 3, and I'm going to use 3 here, my next try. So as usual, we copy 1 down, multiply 3 by 1 is 3, get 0 here, right? 3 by 0 is 0, 1 plus 0 is 1, 3 by 1 is 3, and yes, 0. So this equals to 0, so this is 0. So my first 0 is actually x. My first, like I think a factor is x minus 3, and my quotient is what? X squared, and there is nothing, no coefficient of x, because we have 0 over here, right? And there is a coefficient equals to 1. Well, actually, I factored everything. I'm going to continue factoring it. But instead of checking the roots, I'm going to try to solve now my second parenthesis, which is x squared plus 1. If I start solving it, x squared plus 1 equals to 0, I'm going to get x squared equals to negative 1. And we do remember from somewhere in the beginning of the class that when x squared equals to negative 1, which like contradicts our common sense, we are going to invent a new number I, and that's going to be plus minus I. So what I'm going to do, guys, I'm going to write down x minus 3, x minus I, my first 0, and x minus I, my second 0. I'm going to simplify it a little bit. I don't have any space here left, so I'm going to write it down like x minus 3. And for this one, I'm going to write down x minus I and x plus I, because I have minus I. Well, so I did factor my polynomial completely. I'm going to consider one more example to show you how everything is working, and let me check if I have it the correct thickness. Example number 2, x cubed minus 2x squared plus 3x minus 2, and I want to factor it completely. Well, again, I'm going to do synthetic division. What I see is that my coefficient is minus 2. Here, the coefficient is 1. So it's actually 2 over 1, but because 1 is always like by itself. So I'm going to have possible zeros plus minus 2 and plus minus 1. And these are rational zeros. So we understand that normally polynomial can have rational zeros, irrational zeros, and also complex zeros. This method is showing only rational zeros. Probably polynomial has no rational zeros. Then we check all these numbers and we get none of them working. But let's hope in best and that 1 or 2 of them is going to work. So I'm going to copy 1 here, minus 2, 3, and minus 2 again. And I'm going to check 1. Well, again, I always start with 1 because it's easiest kind of root to check. So I copy 1 down, 1 by 1 is 1, minus 2 plus 1 is minus 1, minus 1 by 1 is minus 1. Here I have 2, and 2 by 1 is 2, 2 plus negative 2 is 0. Yes, that's going to be the factor. So I'm going to write down that x minus 1, I factored it out. That's my divider, right? And my quotient is over here, and that's actually what? X squared minus x plus 2. X squared minus x plus 2. Well, now I'll need to factor this expression, but because it's a quadratic trinomial, I'm going to use the formula to factor it. Using the formula is going to give me what? X1, 2 equals, well, minus b, which is minus 1 already, so it's 1, plus minus square root b squared, which is 1, minus 4, a is 1, and c is 2, and divided over 2a, is 1, so divided over 2. That's 1 plus minus what I have over here. It's 1 minus 8, which is minus 7, right? Square root of negative 7. I'm going to modify it a little bit. Let me shift my board actually this direction. So guys, what is square root of negative 7? We remember that square root of negative 7, so from somewhere from the beginning of the class, it's square root of 7 multiplied by I. I'm going to write down that square root of negative 7 can be represented as a square root of 7 by square root of negative 1, which is supposed to give us plus minus square root of 7i. And denominator is 2. Unfortunately, we cannot simplify this any further. My choice of numbers was not very good. So I'm going to just write down factored form for this polynomial, p of x, and that's going to be x minus 1, my first parenthesis, and then x minus the root with plus 1 plus square root of 7i over 2. And x minus root with minus square root of 7i over 2. And that's totally factored form. Well, guys, what is interesting? Do you see that we got roots over here are complex conjugates? Complex conjugates means that one has plus in front of imaginary part and one has minus. Well, this is going to be always the case if your polynomial has real coefficients. In our case, they're just natural numbers, or let's say integers. But even if they're real numbers like 2.1 or square root of 2, they're still going to give you complex roots conjugates. Why does it happen? Well, if you have non-conjugated complex root, then when you multiply it into this long multiplication, eventually you are going to have a leftover I. And the polynomial does not have no I, means that it cannot exist. Okay, let's talk a little bit now about multiplicity of zeros. Double check where we are. Okay, multiplicity. Imagine that somebody gives us polynomial p of x and he factored it already, and it has factors x squared, x minus 1, x plus 3 cube. Well, what are actual factors of this polynomial and what are zeros? Well, though we write down x squared, we actually mean x multiplied by x, right? Then x minus 1, and then x plus 3, x plus 3, and x plus 3. That's x plus 3 cube, right? So if we start counting zeros, so writing down what are zeros here, which numbers are turning this polynomial into zeros, we're going to see that x equals 0 is going to turn it to 0 because of this x. But also there is one more x, and that means that actually we are going to have two roots of zeros. When you have two same roots, or two same parentheses when you factor it, you are going to say that multiplicity of your polynomial equals the number, the root is repeated, number 2. Well, x equals 1 is not repeated, right? The 0 of these parentheses, that's just like multiplicity equals to 1. And x equals minus 3 actually is repeated 3 times, right? It's minus 3 minus 3 and minus 3. Multiplicity is equal to 3 times. Well, now let's count how many different roots do we have. 1, 2, 3, 4, 5, 6. 6 different roots. I mean, not different, but like in total. The 3 of them are not different, they are minus 3, and 2 of them are zeros, not different too. What is net degree of this polynomial? Well, what is degree of x here? Well, let's look. That's x squared, right? If you multiply it by this x, that's cube. And if you multiply by this, maximum is going to be cube 2. So it's degree 6. So polynomial of 6 degree has exactly 6 zeros. And that's going to be the case for all other polynomials. We're just supposed to count zeros which repeated several times as kind of like different zeros. Okay. Now, one more thing in this section I want to explain is how to find a polynomial with specified zeros. Finding a polynomial with specified zeros. Well, for example, somebody gives me, I want a polynomial with 0, 1, next 0, 2, and next 0, 3. Well, you know that if these 3 numbers are zeros of some polynomial, then you can factor this polynomial into x minus 1, x minus 2, and x minus 3. You also can have a coefficient here. From where does it follow? It follows from this theorem, from theorem of like complete factoring theorem. So if polynomial has zeros, here it's about complex zeros, but real numbers are complex zeros too. Then if they are zeros, then polynomial can be represented in factored form. Well, we can have a coefficient here, and that's going to be my polynomial. Well, we can simplify it a little bit. Let's assume let's set a equals 1. Let's set, I don't have space here, okay. You can set it to a different number. If the problem requires you to have a first coefficient equals to 5, for example, then you're going to have a different number. But for now, let's set it equals to 1. And then multiply everything here to get the polynomial actually. So if I multiply this first and second parenthesis, I'm going to get x squared minus 1x, and x by minus 2 is minus 3x, and minus 1 by minus 2 is plus 2, and multiplied by x minus 3. And I'm going to just multiply everything by x first, and that's x cubed minus 3x squared plus 2x, and then multiply everything by minus 3. Minus 3x squared plus 9x, and minus 6. Okay, now I'm going to simplify it a little bit. My pen is stops working suddenly. So it's x cubed. We have not much left. Minus 3x squared, and minus 3x squared is minus 6x squared. And 2x and 9x is going to give me what? 11x, right? And minus 6. That's my polynomial. If somebody is telling me, okay, I want a polynomial with these zeros and 5 as a coefficient of the greatest factor, of the greatest term, then if they want a 5, you're going to multiply everything by 5 here. For example, I'm going to just use a different color. For example, it can be 5x cubed. Oh, sorry, my thickness is too large. Okay, my 6 disappeared. So, okay, I'm going to just keep black. 5x cubed minus 30 square. 30 doesn't look like 30, right? Something is wrong with my pen, definitely. Okay, we're almost done. So if you multiply this by 5, that's going to be, I think my battery is dead. Okay, guys, I think I'll need to interrupt, and 55x And the last one is minus 30. Well, again, if somebody is asking to have a coefficient 5 over here, if somebody is not asking anything, you can always use a equals 1. Well, basically, guys, we have just one more example, and maybe my pen is going to support me during this next example. So, yeah, no, sorry, I'm going to get a different pen. I'm going to interrupt for a second and get a different pen. Okay, I got a different pen. So one more problem, one more example I want to consider is going to propose some complex roots. For example, somebody is telling, I want a polynomial with roots 2 and root 2i and last root minus 2i. Can we create a polynomial with these roots? Yeah. Well, again, let's assume that a is equal to 1. No one is asking, giving us more conditions on a polynomial, so just roots. And we're going to have x minus 2, x minus 2i, and x minus negative 2i, which is going to give us x minus 2, x minus 2i. And here minus and minus are going to give us plus x plus 2i. Guys, over here, I'm going to use the formula a minus b, a plus b, which is going to turn it into a squared minus b squared minus 2i squared, which is going to be equal x minus 2. And here I have x squared, and I squared is minus 1, 2 squared is 4, and there is one more minus, so it's plus, so plus 4. And I can multiply it and get the polynomial x cubed, I guess, x squared by x, right? Minus 2x squared, x squared by minus 2, and then plus 4x, 4 by x, and minus 8. And that's going to be my final answer. Again, you see that I used complex zeros in conjugate pair 2i and minus 2i. If I, for example, decide to choose, for example, first root 2, second root 3, and the third root just a complex number, then when I multiply everything, my coefficients here, like coefficients which are in front of x cubed, a square, and the first power, can have I. Coefficients are going to be complex. It's not bad, can happen in nature sometimes, but usually we like or we prefer to work with real coefficients. Last problem, which I want you to try on your own, is factor polynomial completely. So solve problem, factor completely. The polynomial is not complicated, and I'm going to give you a little clue how to deal with it. Because the last coefficient is equal to 8, it's not going to be easy to check all these rational roots here. Just like you have plus minus 8, plus minus 4, plus minus 2, plus minus 1, 8 different numbers. This is biquadratic equation. Somewhere in the week 2, we had these equations, and I suggest you to use a substitution t equals x squared, which is going to turn this equation into quadratic, and that's going to be easier to check. You don't need to do this complex synthetic division if you see other methods to do, because synthetic division, it's still a trial method. You try different numbers. But when you have a kind of method which is giving you the answer necessarily, then use it. Okay, I'm going to count to 5 and give you my solution. So, and you can stop the video and try to do it on your own before you hear my solution, of course. So 1, 2, 3, 4, 5. So I'm doing my substitution. Well, t squared, because if I raise it to the second power, I'm going to get 4 plus 2t minus 8 equals to 0. And that's my kind of quadratic equation. I'm just going to use my formula t12 equals what? Plus minus square root of 2 squared is 4 minus 4ac. A is equal to 1. So it's going to be something like this, minus b, and divided over 2a. Sorry, not supposed to be a triangle. 2a, and a is equal to 1. Well, you don't need to write down 1. It's just like I'm writing down two points that a is equal to 1. So what I have under the square root? Under the square root, I have 4 by 8, which is 32, plus because we are going to have minus and minus, and plus 4 is going to give me 36 minus 2 over 2. Well, square root of 36 is plus minus 6 minus 2 over 2. And I'm just going to have two nice kind of real numbers, right? So first one, 6 minus 2 is 4 over 2 is 2. And the second one, minus 6 minus 2 is minus 8. Minus 8 over 2 is minus 4. Well, you see these two roots are actually kind of nice real numbers. And I'm going to continue solving because they are not my x's, they are my t's, right? So I'm going to write down that my t1 equals 2 equals x squared, right? Because t was x squared. From where I'm going to conclude that x equals plus minus square root of 2. Again, extracting a square root of both. T2 equals minus 4 equals x squared. Well, here I'm going to have x equals plus minus. Square root of 4 is 2, right? And square root of minus 1 is equal I. And I got like 4 solutions. Now I'm going to represent the factored form of this polynomial. P of x equals x minus square root of 2 using the plus value. X minus minus square root of 2. X minus 2i. And x minus minus 2i. I'm going to simplify it a little bit, just playing with minuses. X minus square root of 2, x plus square root of 2, and here x minus 2i, and x plus 2i. So that's completely factored form of the polynomial. Because my polynomial has coefficients which are like just natural, even not natural, but integers, I'm going to have complex conjugates here and complex conjugates here. The same reason. If you do have like just irrational number like square root of 2, not a complex conjugate with other roots, eventually it's going to appear into a final polynomial you have like over here, x to the power of 4, 2x minus 8. And if your coefficients don't have any square roots of 2, most likely, if you do have solution of square root of 2, it's going to have a conjugate. Okay, that's all for this section 5, I think, and please do your homework, okay?